let me skip back. We learned about the module, and now it's time to learn about what we learned in this session. So this is the learning objectives. After the sessions, you should be able to characterize distributed parallel computing in HPC, for example. Now, and there are some more listed, and I don't read them. You can read them later, but these are the key motivation. Yeah, you should understand a little bit the basic system architectures, and you will get already an example for parallel computing using a vector addition. Okay, that's what will happen now. But let me start the motivation. Why do we need HPC? Therefore, we have to talk a little bit about the scientific method. What is the scientific method? It's the method how we do science generally. Typically, we either make an observation that is really interesting, or we think of an interesting question. No? And from that, we formulate a hypothesis, and then we develop testable predictions. Then we gather data to test the predictions. We may go through this cycle multiple times until we are satisfied until we got and tested that our hypothesis actually is kind of proven by this experiment that we did. From this, we typically develop general theories, and then the whole cycle repeats and so on. Now that's how this works. And for decades, the pillars of the scientific method were theory and experimentation. Now, so of course, you need to think about things, you need to consider certain aspects, you can develop theories, and then you have to make observations and you have to gather data or make an experiment, in fact. So now, in a modern perspective, we have also this strong pillar, which is simulation. This is basically computer-aided simulation. And we also have big data analytics. I'm not talking about this one, but I will be talking about simulation. Why is that? Well, computer-aided simulation replaces the traditional experiment more and more. And our computer simulation is really can be considered to be an instrument that empowers you as scientists, and I consider you to be a scientist now, to conduct these kind of experiments. The advantage over a real experiment is that you can manipulate arbitrary model parameters. You can get a high degree of reproducibility when you do a simulation. You rerun it again with the exact same parameters in the computer, you should get pretty much the same result. And you can conduct great experiments that are in reality infeasible due to ethics, risks, or costs. Like what happens if a nuclear power plant explodes? There should be no one that wants to do that in real life, but in a computer simulation, you can do it. And we should do this. We should figure out what happens to consider the risk. Now we can see what does poison to human cells, brain neurons, and so on. You can also predict the future. And all of these things, they are done as part of simulations. Okay, so we simulate the reality somehow, and we use this to replace the experiment. However, the problem is that simulation is compute and memory intense. For example, if you have billions of neurons for your brain, you need a lot of memory. And if you have a plane engine, it consists of nowadays many triangles, very small triangles that kind of mimic the material that you want to simulate. Then you have AI models that are nowadays quite complicated and sophisticated that use thousands of GPUs to train. And all of that comes with some deadlines for the simulation. Certainly, if you, for example, want to do the weather prediction of tomorrow, you want it to be completed before tomorrow. Otherwise, it's kind of useless for you. Now, the problem is how can we cope with this huge demand for computer and storage resources? A single PC server workstation is not able to solve such compute tasks. So you need performance, and then you need high performance, and that is why we need high performance computation, which is what we are doing as part of this course. So how is the scientific method related to simulation? Let me recap that. So the simulation allows me to model real systems to gain new insight. It can be also, what I didn't mention, a real instrument, by the way. So simulation can be used to, for example, simulate something that happens by modeling the real world, but at the same time, you can also use a real instrument, such as, let's say, a microscope ultra fast microscopes with high resolutions, and you fill in this data also into simulations. Okay, so they can not distinguish a real instrument and mix it up with a simulation instrument that is happening in a computer, yeah, but these things are connected. Okay, so I can simulate something feeding in data from a real instrument and consider this to be my computer instrument. Yeah, and you use this to validate refined theories, to identify new phenomena. And in terms of classical computer science, if you are not using big data analytics, we typically based on modelings with physics, hard facts, and real-world simulations. You need to drive forward the frontier of science, massive compute resources actually. So we talk about exascale computing. That seems to be a very big scale, more about that later. Yeah, and data-intensive sciences like climate and this kind of instrument-driven observational data kind of sciences, they impose other challenges to data handling, but they also fall into this kind of category of computer-aided science, I would say. So now talk a bit about high-performance computing. So what is HPC? It's actually the field that provides massive compute resources for a computational task. And normally this task would need too much memory or time for a normal computer to be solved. So HPC is an enabler of complex, challenging simulations and programs. And now we talk about supercomputer. What is a supercomputer? It aggregates the power of many compute devices. In the past, you had really big systems. Here is one where we see that's taller than 2 people. It was a monolithic computer. And there were also monolithic computers that actually filled halls. Nowadays, we actually, instead of doing a monolithic computer, we kind of connect together thousands of servers, and we speak about a cluster then. Okay, so we cluster them together, and these are just very powerful individual server components that are connected with a strong network. For me, in terms of comparison, a car is to Formula One like a computer is to a supercomputer. And in fact, I would say it's not, I mean not here a Formula One car, but I mean the whole Formula One, if they would kind of work together. So a supercomputer consists of many fast cars. So one of the fastest supercomputers of the world is, for example, Fukaku. It's at the Weekend Center for Computational Science. And this is here an image, a rendered image that shows you the big hall. And the person would be as big as, I think, like this. And you see a lot of cabinets here. And it consists of 160,000 nodes, which means independent servers and 8 million CPU cores. It has a peak performance of 540 petaflop, which means 10 to the power of 15 is petaflop. 5 petabytes of memory, 150 petabytes of hard disk space storage. So that's a lot where you can run nice computer games. In fact, you could run probably more than 160,000 computer games at the same time. And it comes with a price to set this up, this machine in this hall and advance the software stack and do a little bit of work on the applications. It's needed about 1 billion. So 1 Milliarde Euro basically, or dollar, to basically build the system up and make it running. And it consumes about 30 megawatt. So if I take a rational price, this corresponds to about 30 million euro per year in terms of energy budget. No, not much if you consider that the whole machine was about 1 billion. So that's a huge effort, but people are doing this because they see the advantage and benefit of using computer-aided simulation for all their experimentation. And if you look inside, some systems look really nice. You have these corridors with the nice lighting. And how do you connect to such a system? Well, now the advantage and the simplicity is that the user, they can sit at home, in home office, they can sit in whatever office they like. They connect over the internet to the data center remotely, and then they typically type in some commands, which is what we will do in the first session. And then stuff will be executed on the nodes on the system, and looks all very abstract. This is a little bit, I would say, the challenge, because people, they type this in on the command line. They sometimes think, oh yeah, it's not a big deal, right? You just type in run something, run it on 100,000 nodes, and the system does it maybe. And then later you figure out, man, this in fact has costed me to run this. It costed me like 10,000 euro. You would never pay for that, right? But virtually this is what your experiment has costed. So this is kind of the difficulty, I would say, because it's very abstract to work in front of a computer and some big machinery is in the back. If you sit in front of this hall, yeah, like this, and you would sit there literally and you would do something like physicists do in, for example, the particle accelerators, you would be clear that this is some big machine and you need to have the appropriate training and you need to kind of be careful with this machinery. However, people often don't see that because it looks so simple as running something on your own machine. Okay, keep this in mind a little bit and be cautious. This is a precious, big systems. This is really a big instrument and it is shared for many users. Okay, anyway, talking about HPC in Göttingen. Well, the GWDG, what is this? If you don't know about it, it's the University Data Center and it provides innovative technology solution, of which one is for HPC systems. We have HPC systems for local scientists, German-wide, and for the DLR, which is the German Aerospace Agency. So this is the new building, the RZG, where a lot of compute systems are housed. And here you see a very nice image of some systems that we have at our Fernmeldezentrale. And in terms of HPC, we integrate research for HPC system and services, and of course training, which is one reason why you are here. So before we go and understand a little bit parallel computing, we need to understand shortly what is distributed computing. So distributed is computing is the field in computer science that studies distributed systems. Okay, that was simple, but what is a distributed system? It's a system in which you have different components and they are located on different networked computers. Okay, so I have here a computer, for example, and here a computer, and somehow they are connected over a network. These things, they communicate and they need to coordinate actions by sending messages, okay? Like you do when you email, yeah? Just when you send an email to another computer, this is already a distributed system. Okay, one computer says, okay, here you have a message, which is the email. The other computer says, okay, I send, for example, this email, and then you get, okay, your email has been sent. And you are happy, and something else happens with this email. These components, these different computer systems and remaining infrastructure, which is a lot more than just computers, they interact to achieve a common goal. In this case, it was the email example. So in the wider sense, there's also a wider sense, this definition what distributed systems are, but let's not go into them. What is the characteristics of a distributed system? It's distributed memory. Okay, you have components that have their own memory. It's, for example, like really you and me. Yeah, we are two people and we can be considered to be a distributed system. We can communicate by talking, by writing us, for example, letters and stuff like this, but I cannot see your thoughts. Your memory is private, my memory is private. Okay, so we can also work at the same time. I can do something different than you do. Okay, at the same time, if sometimes you want to achieve a common goal, whatever that is, building a rocket that goes to Mars or whatever, and do some additional science. Okay, so there is a concurrency of these components, so which is that they compute at the same time. There is a lack of global clocks. That means that my time might differ a little bit than your time. And that happens even if you have GPS clocks and so on. Now, so we might have very slight variations in terms of what time actually is. So if you ask me what is now, we would have a different opinion on that. There's also, in distributed computing, a high chance that components may fail because we have many. Okay, if you look at the world, there are now, let's say, 8 billion people in this distributed system. And at any time, it can happen that people fail. They could be sick. Something could happen. They could be disconnected from the network. They cannot communicate. And in real world, that of course means you could be disconnected due to power outage, due to networking issues, or DNS probes, as we have learned. So here's an example of a distributed system, how this looks like in a distributed program. from the hardware side, so we have multiple computers that are connected to a network. So that's the way where they can exchange their messages. And in a computer, you have a processor, you have your own memory. You can have multiple processors and multiple memories, of course. And now our distributed program runs on this system. We have to have a view, we have to map our application somehow to this system. So you could have, for example, on this computer here, 2 programs. And these programs, they exchange information using messages. At the same time, you could have another program running on this computer over here, and they communicate, right? So this could be, you know, a mail application that tells another local mailer, please send a message, and then it goes to this computer, which is the mail server on the other side. Now, and then we have at the same time not only one application, but we have many applications. Here's another program from another application. And by application, I mean really this kind of goal-oriented set of programs that collaborates to achieve a certain goal. Okay, so what we see is also that since there are many computers involved, that a distributed application or an algorithm, it may involve different not only different computer systems, but these different computer systems could be equipped with different hardware. And they could be provided with a different software and hardware stack. Okay, you want that your mail works from Apple systems as it works, for example, from my Linux system or from Windows 11. So there are a lot of distributed applications and algorithms that I could go through. But like the internet and telecommunication network is a great example. Internet of Things, there are a lot of different algorithms on that side over here, but I'm not going through them. So then we have cloud computing. A lot of people ask about the cloud nowadays. So what is actually the cloud? Well, it's people, there are different definitions about it. This is kind of my view on it. Cloud is the on-demand availability of computer system resources, which can be data storage and computing. Okay, and this is provided a little bit like power comes from the electricity grid. Here comes computing from the cloud over this kind of cloud system. So how are these resources provided? They are provided by data centers to many users over the internet. And then there are additional systems that brings cloud closer to users. And there are a lot of applications like Dropbox, Google Mail, and Office 365 as an example. We have different infrastructures, and there are platforms. So there are infrastructures, which is the hardware side, and then it can be platforms that provide certain level of kind of APIs, interfaces for certain tasks, for storage, for example, for identities, databases, and so on. And you have lastly applications on the highest level that are provided to end users. So challenges when you use distributed systems or when you are developing them is when, in terms of programming, there are a lot of new programming mistakes that you can make. It's very difficult to think about all the cases of concurrency. So I'm here in this code and you are doing this. So how can we not get stuck, for example, in this communication if there happens mistakes and messages get lost and all that? So there is a lot of this coordination, and it's very hard to debug this, particularly if you talk about thousands of nodes where the communication takes place. And you have difficulties often to get this global view. So what is everyone doing? Not only because there is this global clock lacking, but because you simply have this huge number of nodes that are interconnected, and they somehow need to give you this data, which is tricky, of course, for debugging. Good, it's resource sharing. We have systems that share resources between all users. Not only your program runs, but many programs potentially. We have scalability. We want to grow with the requirements, which can be the number of users, the data volume, or the compute demand. But at the same time, we want to retain the performance level, which is response time. This requires us to add hardware, for example. We have faults in the system, which means we need to detect, mask, and recover from those failures. Yeah, if there are 1,000 systems, at any time there will be 1 or 2 down at least. It's kind of the normal mode of operation. A fault is not abnormal, it's normal. you have this heterogeneity that you have different hardware and software. We often don't want to care about where the code and data is, which is about transparency. And lastly, we have security. So there is some issues when you talk about a distributed system. It's easier to break in. You need to harden a lot of nodes. You need to make sure that this message exchange happens securely. So, and now let me give you just a second, because I want to ensure that my slides are the right ones. So now let's go talk a little bit about parallel computing. So what is parallel computing? You do many calculations at the same time, so simultaneously, or you run many processes at the same time. So what is a process here? We mean what the operating system thinks about a process. It's like a little program that has its own thread and it proceeds and it executes certain commands. Okay, a process is independent from other processes. So that's sometimes used. More about that later. But for now, you can think of either programs, multiple programs that run at the same time, or you do many calculations at the same time. And the main characteristics of parallel computing over distributed systems is that your goal is to improve the performance for this overall application. That means you want to solve problems either within a deadline, or with increased accuracy. And this increased accuracy comes more need for compute power. And then again, that means your deadline should stay the same, basically. So the application system must coordinate, in this case, the otherwise independent parallel processing. So you have not independent processes, but processes that work together. And there are various programming models for parallel applications that you can use, such that they can coordinate and work together efficiently. So different architectures exist that allow me to speed up computation. So we may use a distributed system. Yeah, a distributed system is inherently having multiple compute CPUs, and then you can, of course, do multiple computations at the same time. But there are also other architectures that allow me to do parallel calculations. For example, GPUs. GPUs in the strict sense are also parallel computing, even though if you just may use one GPU, inside the GPU, there's a lot of things happening at the same time. So that from hardware perspective, there are different levels of parallelism. So you can, for example, work on bit level. That means you process multiple bits at the same time. That happens, for example, in your arithmetic logical unit. You may process multiple instructions in your CPU at the same time. You may work on different data and do the same computation at the same time. And you may run different computations at the same time, which means on the task level, we have some parallelization. So let's talk a little bit about bit level parallelism, which is what happens with SIMD, which is single instruction, multiple data. What it does, it applies the same operation on multiple data. That's the idea. So for example, for vector addition, you want to say something A equals B plus C, where A, B, and C are vectors. And then how you do that? Well, you add each components. So the ith component of A gets added to the ith component of B, and it becomes the ith component of C. So in fact, if you have a vector of 8 elements, it looks like this. A consists of 8 different values. B consists of 8 different values. Then, of course, you add this value plus this value plus this value. And there are instructions that allow you to do this. For example, AVX 512 allows me to do this with floating point, double precision floating point numbers. And all of these additions happen at the same time. So that means I get 8 additions done at the same time instead of just 1. So that is parallelism on the bit level. So then when we talk on a higher level of parallel architectures, there are a mix of 2 paradigms. First of all, there is our distributed system again, where we have distributed memory, right? So we have a computer system here that has memory, and it cannot look into the memory of this system. Here, it's very important that we can exchange information rapidly. So messages over the network must be communicated quickly. And we program this system using message passing, naturally, because that's the way we exchange information. Then we have also shared memory systems. What does it mean? Well, we have here one memory which is interconnected, in fact, with a very good network on our system to multiple processors. In fact, these systems, they look quite nearly identical, I would say, on a high level, because inside a processor, we have also a local cache, which could be considered as a memory. The main difference between the systems is that here, each computer is independent from the other computer. Here, if one computer or one processor crashes, typically your system will fail. And here, the network is much, much faster and optimized to access the memory. And the memory here has a way to ensure that when one process accesses it, that all the other processes know the same state of the memory, kind of, they would see a single memory, while here the memories, they are inherently different. Okay, it's very difficult to scale up such a shared memory system to large systems because of these properties that you want to ensure that this memory is consistent. And cache covariant is the proper term, but it doesn't matter too much. And you program such systems typically with tools such as OpenMP, which is a way of accessing the joint memory, as this makes us life much easier. So let's look a little bit more into the hardware. Well, if you look at a Xeon Platinum system, Cascade Lake, I suppose that's one that we actually have available at GWDG. And this system, this single microprocessor has a lot of cores, and they are here interconnected with this kind of ring, 2D ring topology, which is the network between these cores. And each core can run one program, one process at the same time, or one thread to be more precise. And if you look up the performance it has, depending on the frequency, you would get that this system has 2.2 teraflops. And it has 6 memory channels, which is a throughput of 130 gigabytes a second, and it needs 205 watts to drive these Platinum processor. Each core has 2 of these AVX units, so that means we have this vector parallelism, and then we have this parallelism on this ALU level, where we can multiple instructions at the same time. It's a very complicated architecture. I don't want to go into further details, but inside one core, there is a lot of things going on. Yeah, it has very heavy cores, and this system is optimized for latency. That means anytime in your code, you need to make a decision, like with branching, with if constraints or something like this, the system can rapidly handle those and tries to give you the answer in as few CPU cycles as possible. Then on the other hand, we have GPUs as one accelerator technology. This kind of accelerated computing is outside of this course, but we have, of course, also some courses that kind of give you some training in this. But I would say the concepts between those two systems, they are to some extent transferable. What you learn here is useful for this other course and vice versa. There's a lot of similarity, but there's at the same time also some dissimilarity that I want to go through. So in terms of flops, this system has a lot of independent systems. Let me show. Each of these kind of points here is four cores that work together. Now it has a very much faster memory throughput, so it's 10x faster in terms of memory throughput. It just needs twice the amount of watts. And inside the system, you will have 128 of cores, while each core can run 32 operations at the same time. No, so you have these multiprocessors, and we talk here about cores, but these cores, they are not fully independent. Okay, so they are depending a little bit on this instruction stream, and in fact, so you have 4,000 cores. So that's about, to compare it with this system, here you have 28 cores. It's about 100 times more. No, 10 times more memory, 100 times more. But overall, for scientific applications, oftentimes what you find is that one of such a GPU is about 2x than a system where you have two CPUs deployed. Okay, so 400 watts, in fact, it's like 400 watts here. System then perform quite similar. Reason is it's very difficult to work on this system, also due to this infrastructure here. These cores are very simple. They are optimized for throughput. They have a very deep pipeline, high latency, and it's very costly to run programs. And these systems, these accelerators, they are plugged in as a graphics card, basically inside your computer system. So it is a little bit like distributed computing. You have inside your computer already another system that you can tell to do this, do that. And that is kind of depending on the CPU and the basic system. So what is now a parallel program? It runs on parallel hardware. In the strict sense is that we have a parallel application that coordinates some kind of concurrent processing. Okay, so we talked about our system, and our processor, in fact, provides all level of parallelism. So we have inside our multiprocessor, microprocessor, we have multiple cores. Inside a core, you have this kind of caches, and each core can work independent of the other cores. Then inside a core, we have the single instruction multiple data system with this instruction set such as AVX and SSE, in fact. And then inside such a system where we have two microprocessors, so you may have multiple microprocessors in one system, you may deploy also multiple GPUs at the same time. So there is a lot of parallelism going on, which makes this difficult to handle the overall system in terms of heterogeneity. So now I want to ask you briefly in your breakout group to think about your application. Maybe you have already an application in mind if you come from GWDG Academy. If not, talk about something where you think parallel computing might be interesting. Describe this use case briefly and think about those two sub-questions. What computation is performed in parallel? In fact, for example, if I do image analysis, I can look at two images at the same time, but I may not look in these pixels inside the image at the same time, okay? So it depends a bit on your use case and which architecture or hardware would you like to use for it. Okay, now in 5 minutes, so that means 7 past 10, we go on. I will rush a little bit. Okay, cool. If you have further feedback, put it in the chat or further suggestions. Challenges. First of all, in parallel programming, we inherit all the challenges that we get from distributed computing. Additional performance is a problem, because we want to get performance, so we need to optimize it for gain performance. And it's really difficult to debug 1,000 concurrently running processes. To make sure that the load is distributed evenly across these processes is difficult too. How can you write test code for grand challenges, scientific grand challenges? Let's say, for example, I simulate the fusion reactor. Is the simulation correct or not? Well, since no one has ever done this before, maybe it's difficult for you to write a proper test. So performance engineering, which is kind of part of the optimizing code, is a main agenda for HPC. It's covered in this course. Scalability is a problem because it's much stricter than distributed system. We have two new types of scalability here. Strong scaling is where you have the same problem. More parallelism shall improve performance, so reducing runtime. Weak scaling means you increase the data, but you want to retain the time to solution. So you increase data and you increase the hardware at the same time, and you want to keep the runtime the same. More about this later. Typically, in terms of environment, we have bleeding edge environments with the newest technology, varying hardware and software, obscure special purpose hardware. And that means we have limited knowledge to administrate, use, and compare performance. That makes it all difficult. In terms of programming, let's quickly investigate how to create a parallel program. We look into sequential code to compute vector addition. And then we look how we can automatically, magically parallelize this code. So here is a sequential CPU code. Imagine you want to do a vector addition. A, B should be stored in C, and I would say somehow I need 8 elements that I want to add. Okay, here's the input in C code, and I have my vector addition function here. And what I do a loop, and I just do the additions for these different kind of elements, indices. Okay, we have this in the same file. This is a single source file. I compile it, I run it, it works, of course. So now the magic comes with OpenMP. It would be, of course, great to say, if I have this independence between the different elements, I say magically, please parallelize this for loop. Okay, this is what I do here. I tell my compiler, please parallelize this for loop. And then what it can do is it can run these 8 additions at the same time. So that's already a level of parallelism, and that's a very easy, a cheap way, but it's typically much harder than this trivial example. Okay, this is really a trivial example to show you how nice things can go magically. Then you have other concepts that you will learn this week, such as message passing, where you send a message which contains a header, like sender, the receiver, and certain data types that you send, and the data from memory to another program. And here, you, as a programmer, you have to explicitly say, I want to receive a message, like an email, for example, or I want to send a message with certain data. So this is now explicit. It's not automatically than before. And how do you know to whom to send? The advantage of this programming model, typically what you do is you say, you enumerate your processes from 0 to n-1, so 32, for example. And then you say, I'm process 0, I want to send to process 5 something. And a message passing program will run on our distributed system, such we saw over here. It may execute the same or actually different code. So we can have different computers that run different programs or the same program, but they are in different positions inside this code, and they run at the same time. Okay, and just to show you quickly how this works, in my single code, ESC, but it works in Java similarly, I can say, which process am I? I know I'm process 0, then I send a message to process 1, 18 bytes, here is this message. And then if I'm process 1, I say, give me the message from process 0, and then I print it. So that's 2 guys basically exchanging messages. There's so much more to this that we will learn during this week. Now, and in terms of parallelism, what will happen? Process 0 runs the code, and at some point it says, if it runs this branch because it's rank 0, sends the message, and another process that runs maybe on the same node, on a different node whatsoever, says I'm rank 1, receive from 0, and then somehow the message from here, this main memory gets into this main memory of this process, and then it is outputted. Now, this is very tricky, and of course, this process 1 cannot proceed until it has received the message. That's the idea. So you say receive, it has to block, it has to wait until the message is received. A sender may possibly proceed because it just says my message has been sent. Good. So to wrap up, when we talked about computer-aided simulation, we mean actually computational science. It's a multidisciplinary field using advanced computing capabilities to understand and solve complex problems with mathematical models, computer simulation. It's typically motivated by industrial or society challenges. You may have a single computer, distributed system, or supercomputer. And there are a lot of systems where you can, in computational science, just use distributed computing, such as CERN has distributed applications or bioinformatics applications. Sometimes you need high performance computing, such as the weather forecast or our fusion reactor. And with that, I conclude this session. And if you have further questions, put them in the chat.